Hello everyone, welcome to my YouTube channel, The Physicist. So, in this video, we are going to discuss some important things about light. Okay, so we start with the sources of light. Okay, we start with the sources of light. So, the sun, stars, lamps, these are the things that give off light. They are called luminous bodies. Other objects such as moons, mountains, trees, etc. are the non-luminous bodies. So there are two types of bodies: luminous bodies and another is non-luminous bodies. Okay. Luminous bodies are those bodies which emit light, which are the sources of light, and non luminous bodies are those bodies which cannot emit light. Okay, they are visible only when they receive light from some luminous source and they send the light, the reflected light, back to our eyes. Okay, so whether a body is luminous or non-luminous depend upon the conditions as well as on the material of which it is made. So by changing the condition, we can make substances luminous or non-luminous. For example, the filament inside electric bulb is non-luminous unless it is heated by an electric current. So it glows and it becomes a luminous object. And we know that the bodies emit light at the expense of various kinds of energy. The most common is the thermal radiation. So when bodies are heated, for example, to a temperature of 300 degrees Celsius, they emit electromagnetic radiations which lies in the infrared region. Okay, so infrared region. Okay, we'll see what is this infrared visible UV region actually is. So lambda is about 5 micrometer in the infrared region. The wavelength is about 5 micrometer. So they emit light as a result of thermal motion of their molecules, that is at the expense of the internal energy. So these molecules or atoms of the body vibrate at the expense of internal energy. Okay, internal energy of the objects. So at a temperature of about 800 degrees Celsius, bodies emit visible radiant energy. Visible radiant energy. Okay, and appear red hot. A large part of the energy still lies in infrared, but some part also in the visible radiant energy. Okay, so at around 300 degrees Celsius, they appear white hot. Okay, such heated material are known as incandescent. Okay, incandescent bodies. Not all sources are incandescent. Okay, on the other hand, some bodies can emit light which is not due to transfer of thermal energy into the energy of electromagnetic waves. Emission of light due to supply of energy through the processes other than heat is called luminescence. Luminescence. Okay, so this is due to the supply of energy through processes other than heat. Okay, there are different kind of luminescence um, exists. Okay, um, the advertisements using the neon and other glow tubes are example of. So neon tubes, okay, we know neon tubes is example of electroluminescence. Okay, in this kind of luminescence, charged particle accelerate in electric field. They partly transmit their kinetic energy to the atoms of the gas, which then emit light. So these gas atoms emit the light that is coming from the neon tubes. So these neon tubes are filled with gases. Okay, many living organisms such as fireflies, fish, bacteria emit light due to the chemical reactions. Okay, so this glow is called the chemiluminescence. Okay, so this thing is called the chemiluminescence. Okay, so this is due to the living organisms. Okay, example are in which the chemical reactions are producing such light. Okay, so example are fireflies, fish, and bacteria. And the cold light emitted by the tube lights is a result of photoluminescence. So there is another luminescence called photoluminescence. Okay, the internal surface of tube light is coated with a phosphor material, which under the action of UV light emit visible light. Okay, the TV screens, computer terminal screen glows because of the cathode, sorry, cathode luminescence, which occur due to the bombardment of screen by the high energy electrons. So in these TVs and computer screens, uh, which is not LED screen, which were the uh, that come before the LED TVs. The TVs were big boxes in which there are cathode ray tubes. So these work on the bombardment of screen by the high energy electrons. So these are different types of luminescence and different types of objects which are luminescent and luminous or non-luminous. Okay, so now we will discuss some properties of lights. Okay, so let us now discuss some properties of light. Okay, so we know first property that we are going to discuss is reflection of light. Reflection of light. Okay, we know that when a light traveling in a medium encounters a boundary, it, okay, so when a light that is propagating in a medium encounters a boundary that leading to a second medium, a part of incident light is returned to the first medium from which it came. Okay, this phenomena is known as the reflection of light. Okay, and reflection from the smooth surface is called regular reflection. So there are two types of reflection: regular reflection and second is diffuse reflection. Okay, this is reflection from smooth surface. Well, no perfectly smooth surface exists, so this is very hypothetical thing. A regular reflection is very hypothetical. Okay. Diffuse reflection is reflection from a diffuse or rough surface. Okay, so it is largely by diffuse reflection that we see non-luminous objects around us. The difference between diffuse and regular uh, reflection is matter of surface roughness. So okay, so in the study we generally mean reflection used to mean the regular reflection. Okay, the regular reflection is also called the specular reflection. Okay, there are two laws of reflection. Okay, laws, there are two. One is that angle of incidence is equal to the angle of reflection. Okay, so this is a medium one, so the light way that is coming at the interface of two medias is called the incident wave, and it makes the angle with the normal to the surface I. This I is called the angle of incidence. Okay, and the reflected ray makes the angle with the normal R, which is called the angle of reflection. So the first law of reflection is that angle of incidence is equal to the angle of reflection. Okay, and the second law is that this incident ray, this normal and this reflected ray are in same plane. Okay, so for example in this case they are in the plane of paper. Okay, so that is the second law. The next property of light is the refraction of light. Okay, refraction of light. So when a ray of light traveling through a transparent medium encounter a boundary leading into another transparent medium, part of ray is reflected. So there the incident ray is coming, and some part of it is reflected. Okay, this is normal, and this is angle of incidence, this is angle of reflection, and part of it enters the second medium. Okay, uh, with angle r dash, which is called the angle of refraction. R dash is angle of refraction. Okay, so the ray that enters the second medium is bent at the boundary and is said to be refracted ray. So this is the refracted ray. Okay, this is reflected ray. So thus the refraction means that light ray follows in the second medium a direction different from its direction in the first medium. The angle r dash subtended by the normal of the reflected ray is the angle of refraction. Okay, this angle is also measured from the surface normal toward the ray. Okay, so what are the laws of refraction? Laws of refraction. So the first law is the incident ray and the refracted ray and the normal at the point of incident lie in same plane. Okay, and the second law is the Snell's law. Second law is nothing but Snell's law, which states that the sine of angle of incidence to the sine of angle of refraction for any given two medium is constant. Okay, that is the Snell, and this constant is denoted by a symbol mu, which is called the refractive index. So mu is called the refractive index of the medium. Okay, so let us now discuss in detail the refractive index. Okay, so the refractive index. Okay, so the refractive index of a medium is defined as the ratio of, so let me change the color of pen. So refractive index of a medium is defined as the ratio of the velocity of light in vacuum, velocity of light in vacuum to the velocity of light in the medium, to the velocity of, so velocity of light in medium. Okay, so this is called the absolute refractive index. Okay, so we can write nu, velocity of light in vacuum is denoted by c, and velocity of light in a medium is can be denoted by the v. Okay, so nu is equal to c by v, and sometimes the refractive index is also referred as the optical density. Okay, it is also called the optical density. So high mu, that is high refractive index, is said to have high optical density. High optical density, which means it is denser. Okay, so if there are two medium, medium 1 which has greater refractive index than the medium 2, then medium 1 is called the denser medium, and medium 2 will be called rare. Okay, a rare medium. So high mu means high optical density, and low refractive index means low optical density. So it will be a rare medium. Apart from the absolute refractive index, there is also other kind of refractive index, which is called relative refractive index. Okay, there are different books using different symbols to show this. Some books prefer mu 2 1 like this. This is refractive index of medium 2 with respect to medium 1, and some also write it as this, refractive index of medium 2 relative to first. Okay, and it is defined as the speed of light in the first medium divided by speed of light in the second medium. Okay, so okay, we can write refractive index of medium 2 with respect to refractive index of medium 1 as this. Okay, and this is equal to c by v2, and this is equal to c by v1. Hence we can find that this expression is also equal to v1 by V2. Okay, so this is the relative refractive index. So the numerical value of refractive index is specified definitely only when wavelength is stated. Okay, and it is characteristic of two media, but it also depend upon the wavelength. So unless otherwise mentioned, refractive index is usually given for yellow light. Okay, the absolute refractive index for air under standard condition is, for air under standard condition, the refractive index is 1.00002918. Okay, for light having wavelength, okay, lambda equal to d line of sodium, okay, which is has a wavelength of 5893 Armstrong. Okay, now since the refractive index of air is nearly equal to unity, it follows that for solid or liquid the absolute refractive index and refractive index relative to air differ only slightly. Therefore distinction is not made between them. Okay, so when air is considered as the first medium with respect to which we are taking the refractive index, so relative or absolute refractive indexes will not be distinct. Okay, they will be same. And please note that the refractive index depend only on the substance, but also on not only on the substance but also on the wavelength of light. The dependence of wavelength is called the dispersion. Okay, now next let us consider an important property of light, which is called the optical path. Okay, optical path, and it is important concept in optics. So optical path, what is optical path? Let's see. The shortest distance between 2 points A and B, okay, the shortest distance, which is a straight line, okay, this is called shortest distance, is called the geometric path. Okay, the length of geometric path is independent of the medium that surrounds that path. Okay, when light ray travels from point A to B, it travels with velocity c in if the medium is air. Okay, so light, if the medium is air, it will travel with the velocity c, which is 3 into 10 raised to power 8 meters per second. And if the medium is other than air, then it will travel with velocity v, which is less than c, the velocity of light in vacuum or air. Okay, therefore light take more time to go from point A to point B located in a medium. Okay, so we know that refractive index is velocity of light in the vacuum divided by velocity of light in that medium. So we can say C, we can write C as the distance AB by the time taken, and in the medium we can say it is equal to AB by time taken. Since this time will be different, we will use different symbol T here. Okay, so refractive index can also be written as large T divided by small t, where large T and small t are the time taken by the ray in the medium. Okay, T is time taken by the ray in moving from point A to B, in medium, and t is the time taken by the ray in air. Okay, so therefore we can write t, that is the time taken by the ray in medium, can be written as mu times the time taken by the ray in the air. Okay, so what does this relation means? This relation means that that a ray takes mu times more time to cover a distance AB in a medium than air. Okay, to take into account this delay, we use another distance called the optical length. Okay, optical length. So if a ray of light travels a distance L in a medium of refractive index mu in certain interval of time, then it would travel a greater distance called the optical length in air during the same interval of time. Okay, so in medium of refractive index mu, if the light travels the time length L, okay, so in air it will travel the distance delta. Okay, so we can write delta by L. Now this delta, because it is going in air, will be equal to C into T. T is the time taken by the ray. Okay, so in the same time it will move the distance L in a medium of refractive index mu, and this will be equal to velocity of ray multiplied by time. So this is equal to C by V. Okay, and C by V is nothing but the refractive index. So we see that delta is equal to mu times L, that is optical path length is equal to refractive index into geometric path length. Okay, thus the optical path length is defined as the product of refractive index and the geometric path length. Note that if a ray travels a distance L in medium of refractive index mu, then the optical path length is equal to mu times L. And in a given time, light travels the same optical path length in different media. Okay, suppose that light travel L1 in medium of refractive index mu2 and L2 in medium of refractive index mu2 in time, in the same time. Okay, then we know that it will travel the same optical length, path length. Okay, so delta will be equal to mu1 L1 is equal to mu2 L2. Okay, now let us consider another property of light called dispersion. So refractive index is a function of lambda, the wavelength of a electromagnetic ray or the light. Generally it decreases with wavelength. Okay, so the proportionality is actually the 1 by lambda. Consequently, the light passing through a material medium will be separated according to the wavelength. This is known as the chromatic dispersion. So separation of light when passing through a material medium according to wavelength is called chromatic dispersion. Okay, chromatic dispersion. Okay, so if the light is incident normally, that is angle of incidence is 0, the blue light merely lag behind the red light. Okay, and if the light is incident obliquely, okay, that is the angle is greater than 0 degree, the incident angle of incidence is greater than 0 degree, the colors become separated in space. Okay, so both surface reflecting blue more than red. And with prism, so when prism is used in oblique incidence, then separation is more pronounced. Okay, so the colors are separated and we will have different colors that will be produced. Okay, so there will be different colors. Red will be on the top, then orange, then yellow, then green, then blue, then indigo, then violet. Okay, so when a ray of light falls on a glass prism, it splits into different colors. This display of color is known as the spectrum. So this is the spectrum. Okay, spectrum of the source of light. Okay, so this separation of composite beam into its constituent colors is called dispersion. Okay, so we can define dispersion, the separation of a composite beam into its constituent colors is called dispersion. And the medium which produces the dispersion, so medium which produces the dispersion is called dispersive medium. Okay, and now in last we discuss the dual nature of light. The dual nature of light. Okay, so on the one hand, light appears to be continuous electromagnetic wave. So light appears to be electromagnetic wave of frequency nu, and on the other hand it appears to be the collection of photons having energy E is equal to having energy and momentum. Okay, so it has been found that neither of models can separately explain all the experimental facts. A particle is precisely localized in space, whereas a continuous wave cannot be attributed to a particular location in space. Okay, for example, this is the particle, so it is precisely localized in space. We can say that it is here, but a wave we cannot, because it is continuous and we cannot attribute to it a particular location in space. Okay, thus the corpuscular nature and the wave nature appear to be mutually exclusive. But however, the experimental evidence points out that light behave both as continuous wave and as a particle. Therefore, we say that light exhibit a dual nature. Okay, so light has this dual nature. The reason for the wave particle dualism may be understood as follows. At lower frequency end of the electromagnetic spectrum are the radio waves, whose wavelengths are so large that they spread over a large volume of space. Therefore, energy available at any point is insignificantly small and their particle nature cannot be observed. So radio waves, okay, large wavelength or largest wavelength, okay, so they have the wave character because they cannot be localized to a point, any point. Okay, so these are observed as a wave. Okay, these are observed as a waves but not as a particle. On the other higher frequency side of the spectrum, we have X-rays, gamma rays. Okay, their wavelengths are so short, the wave energy is concentrated on a point of a very small dimension, and particle nature is radially, so smallest wavelength, and particle nature is radially experienced, whereas the wave nature is less noticeable. Okay, the visible region represent the transition region in which both aspects of light can be observed. Okay, in the photon description, the light intensity is given by nh nu. More number of photons will contribute to higher intensity. And in wave description, so this is a photon description. Okay, and in wave description, the intensity is given by the amplitude square. It implies that square of amplitude of light wave at a point in space is proportional to the number of photons arriving at that point. Okay, so the intensity, in other words, amplitude of light wave determine the probability that photon can be found at a particular point in space. So the probability to observe photon is thus proportional to, so probability is proportional to the amplitude square, and thus the ultimate connection between wave behavior and the particle behavior is interpreted. To sum up, so let's sum up here. So light rays, okay, they consist of photons, which are basically electromagnetic wave trains. Okay, we use all the three description, namely rays, waves and photons, appropriately to describe the behavior of light. When light is referred to when light is reflected or refracted by optical elements such as lenses, we mostly use ray description. Okay, and when the light propagates through space or any medium, we use the electromagnetic wave description. Whenever light interacts with matter, okay, whenever the light interacts with the matter, we make use of photon description. So this is all about light. So next time we will discuss the wave optics. Okay, so thank you.